Nice to see you, everyone. Happy birthday, Maxim. And I want to talk in a bit more precise sense. Title is Categorification of Atiyah-Floer conjecture. And this is based on a joint work in progress with Arya Kabadaimi. And I'm now in Tsinghua University in China. And from Vimsa. And yeah. And I'm sorry I cannot present in person because I have just moved to China and there are several formalities I have to go through before going abroad. Okay, so now I want to talk categorification of Atiyah-Floer conjecture. So let me say a few words. What is Atiyah-Floer conjecture? It is 40 or 50 years old, 40 years old conjecture about gauge theory and symplectic geometry. So we compare two kinds of Floer homology. One is Floer homology in gauge theory. So we consider this three-manifold M.
Sorry, Kenji, are we
Oh,
supposed to be?
I'm sorry. I didn't share screen yet. Yeah. I can see my screen, so I forgot. Yeah. Okay. Sorry. So we consider this three-manifold. Yeah, maybe I will show you title again. Categorification of Atiyah-Floer conjecture. And it's based on works in progress with Alcava Daimi. So let me review the Floer conjecture a bit. So one side we consider three-manifold M. So we fix this Riemann surface sigma together with SO3 connection E, whose Stiefel coefficient class is sigma. And we consider three-manifold M. So together with SO3 bundle, so that its restriction to sigma is E sigma. And the boundary of M is sigma. And this necessarily shows that the boundary is actually disconnected since W2 is becomes zero in ambient space, MI. So typically, maybe you can imagine sigma has a two connected component, something like this.
Stiffer with Nicholas. Sorry, the second stiffer with Nicholas.
Second second class, yes. We have this kind of situations. And this is E, and this is E, and this is M. This is sigma, sigma. So W2 is zero on M. So that's typically the case. So now we compare two objects. One is in gauge theory, and the other is symplectic geometry. And in gauge theory, we consider instanton Fourier homology of the three-manifold M. I'm sorry. So M is a union. So let me write a bit more. So we have this, let's see. We have this sigma, which has a two connected component, and you have M1, and you have M2. And so we glue them, you get M. So it's a closed three-manifold. So now we consider this instanton Fourier homology of M with respect to this SO3 boundary E. So that's the following object. So we first consider this space of flat connection of M. So it is flat connections on E of M. Typically, this is a finite set. We can achieve it after perturbations. And we take this chain complex of M. It is a free abelian group generated by these flat connections. Then we consider this boundary operator as Floer did. So this is just the count. So you have this M, and you have this M, and you have alpha and beta here. And you count A is the ASD connections, anti-self-dual, some kind of Yang-Mills connections on M cross R. which is asymptotic to alpha and beta at infinity. And if the index is correct, this is finite numbers, and you take this as a boundary operator, and you get this chain complex. So this is the instanton homology. That's on one side. And on the other side, we consider this modular flat connections on MI. And we take this Lagrangian Floer homology. So what is this? So we take this R of M, R of sigma. This is a space of flat connections on sigma, E sigma. And this is two manifold, and this is a symplectic manifold.
But what do you do with trivial connections?
This is we assume W2 is non-zero.
Okay.
That's why we assume it.
Yeah.
And so we have this RMI, which goes to R sigma. You have a connection alpha, then you just restrict it. And after perturbations, this one is a Lagrangian immersion. So it means that it is may not be embedding, but it's some kind of immersions. So you have this big space out of sigma. And you have this out of my, out of m1, and another space out of m2. And Floer homology, Lagrangian Floer homology. So this is generated. So you have the chain complex. This is just take an intersection point. And Z. And you have a boundary operator. Just count holomorphic disk.
Kenji, how's this
Yeah.
Lagrange spin structure oriented and so on?
Yes, we can prove it is spin and oriented. And the proof I don't know completely clear is that are there any purely symplectic way to have canonical spin structure? During this discussion with Rikobadami, we found that it is spin. And using gauge theory, we can fix appropriate spin structure. But I don't know kind of purely symplectic definitions.
So those are finite dimensional manifolds, or?
Yes, after appropriate perturbations. So I need to kind of make it generic. That's a kind of complexity, but that's technicality. So for this, the Floer conjecture says that if you consider on one side this instanton Floer homology, and on the other side this Lagrangian Floer homology, then they are isomorphic. So this is a SO3 version, and because we are working on SO3 versions, this is somewhat simpler because the space of flat connection on sigma is actually a smooth symplectic manifold. So everything is defined. So we can write down the conjecture. And actually, morally, we know how to prove it, but we have to still write it up. And we proved it in the case this RM1 and RM2 are embedded. But in general, it is immersed. In immersed case, we need a bit more work. But I think this one should be established. Rather, the problem is writing, not mathematical problem. Okay, so now this is the usual Floer conjecture in a simple versions. In a case, so there is a a trivial connection, blah, 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 there are another problem, but that's another issue. And today, I want to talk about its categorifications. So there are two kinds of categorifications, one categorification and two categorifications. So I want to start with one categorifications. So one categorification, so we want to define symplectic side of the category and gauge theory of the category, and I want to say that the categorical equivalence. And what is this symplectic side? And first I want to explain this gauge theory side of the category. I want to define one category G of sigma. So sigma is a two manifold. So how do it? So we first take its object. So the object of this one category is a three manifold M whose boundary is given sigma. So this is again, so you have this sigma like this. So this M, together E of M is an object. Then the one, so morphism is, morphism linear space is rather, you can see. So if you have this M, then suppose you have this 2M, right? So you have this 2M, M1 and M2. So you have two objects in this category. Then the morphism is nothing but this Fourier chain complex of this M, right? You take this three manifold and you take the Fourier chain complex. So you get this vector space, and this is a kind of chain category, right? So so the morphism space is an abelian group with a boundary operator, and so one can say that this has a you can compose this two morphism space, blah blah blah. Roughly composition looks like this, right? So you have this. You have this M1. And let's see. Yeah. Right. So you have this M3. Then this way is a bit complicated to write, right? Let me see. Yeah, maybe I will write it later. Sorry. To that, so what I need to know is that this you have G sigma M1, M2, then G sigma M2, M3. Then I want to compose it to get G sigma M1, M3, right? So this is this should be chain map. So this should be the category. But actually, we can do a bit more. The claim is that this category, G sigma, is actually an infinity category. So we have, yeah. So we have this higher composition map, MK, so that you have M0, M1, MK minus M1. You have this K plus 1 tuple. Then you have this morphism. So you have this alpha 1, alpha K. Then it should go to this composition. So alpha I, let me define it. Alpha I is a flat connection on Mi minus 1 joined Mi, right? So you have this K flat connections, and you should get this linear combination of the flat connections. So this is and then this higher composition should satisfy so-called infinity relations. And I explain how to define these infinity relations. So the idea is to use a family of Riemannian metric on certain four manifold. This is four manifold. And we use this anti-self dual connections on it to define these operations. So I will explain what is this four manifold. So let me consider the first, the most interesting case. If you have this three, so Mi, boundary of Mi is sigma, right? You have three manifolds which bound sigma. So I want to cook up this four manifold, X, M0, M1, M2. So we construct it in the following way. So first we consider this domain D, this domain. This is exactly the domain I draw. So it is a domain in R2. So it has three ends, and it has a three boundary. So this is so we take this domain, and we multiply this domain by sigma itself. So this is a four manifold. And this four manifold has a boundary, which is a three copy of R cross sigma, right? You have three boundaries. So now, So we take this, so we grew, so here we grew M0 cross R, M2 cross R, M1 cross R. So you have this domain cross sigma. So you have the three ends. Then M0 cross R has a boundary. So boundary M0 is sigma. So this guy has a boundary R cross sigma. So you glue them here. And M1 cross R has also a boundary sigma cross R. So you glue them here. And M2 cross R has a boundary, you glue them here. So you have a manifold X, which has a, then this X has a no boundary. However, it is non-compact, and its end is the following things. So if you remove this some compact set from X, you have the three copies. So let me draw a picture again. So we have this picture, right? Cross sigma, and you have this M1 cross R, and you have this M2 cross R, and you have M0 cross R. So the infinity is, there are three infinity here. So this part you already grew. So here you already grew, so it has no boundary. But if you go this way, then you see that M0 glued by sigma cross R. M0, sorry. M0 glued with M1 cross R. So you have the three end, which is just the kind of mi plus 1 cross R. So that is this four manifold looks like. Okay, so you have this four manifold. So that outside of compact set, outside the compact set, it looks like a union of these three. M0 cap M1 cross R, M1 cross M2 cross R, M2 cross M0 cap R. So it is something like this. And then, so we consider A1. So A1 is a flat connection on M0 glued M1. And A2 is a flat connection on M1 cross M2, and A0 is a flat connection on M2 cross M0. So you put these three flat connections at infinity. Then on this four manifold, which we fix Riemannian metric, we consider, so the boundary condition being that are asymptotically boundary conditions, we consider a set of all anti-self-dual connections on this four manifold, whose asymptotic boundary condition is this three, A0, A1, A2. And if the index is correct, we can count its number. And this is this M2 product. So you have this product structure. So yeah, I mean, so I try to write down the picture, but if you just write it, sigma as disconnected, it's a bit more cumbersome. But basically, it looks like this. So you count some number of instantons. Actually, this is some variant of, I think, Donaldson invariant with Floer homology as a boundary. So this is the M2. So I want to show you what is M3 here. So to define higher operations, we consider four manifold. So we consider four manifold. So you have this M0, M1, M2, M3, whose boundary are all sigma. Then we consider four manifold together with one parameter family of Riemannian metric, GT. So to cook up such four manifold, we proceed in a very similar way as follows. So we first take this one parameter family of domains in R2. So you see that this picture, maybe this picture is something like a flattening of this, right? You have this graph, right? So you start from this very long edge and to other thing, and this go to this shrinks, this part shrinks, and then you have this one edge, and then it goes the other way. So this is the R parameterized family of domain in R2. In other words, it is R parameterized family of Riemannian manifold, two-dimensional Riemannian manifold. Then so we grew this one parameter family. No. We first multiply this guy with sigma. So it is this interior. Then it has a 4 boundary component. So we grew M0 cross R, M1 cross R, M2 cross R, M3 cross R to each of this boundary component. So at the beginning, you have this one, right? M0 cross R, M0 cross R is here. And then M1 cross R is here, M2 cross R is here, M3 cross R is here. So this is actually a diffeomorphic to each other, but your metric, Riemannian metric depends on this T. So you have this, first this guy became longer, and then finally this horizontally gets longer. So we have one parameter family of Riemannian manifolds. Then what we do is very much similar. So this guy has 4 ends, which is a mi, and mi, sorry, 4 ends, and which is mi minus 1 glued mi plus 0 infinity, right? So you have 4 ends, and we have a flat connection ai on this mi minus 1 cross mi. So we consider this ASD connections on this 4 manifold X, but together with moving T. It means that for any T, you have a modular ASD connections, and you take the union over all T. And this AI and A0 is used for the boundary conditions. So you have some modular space, and we count this modular space, then obtain some numbers. And that number is defined as M3 operations. So this is this next step operations. And actually, we can use it to show that M2 operations is associative in a cohomology sense. Because so we see this picture is very much similar to the kind of associativity of product in Lagrangian Floer theory. So we have this metric. Then as t goes to infinity, then this part gets to infinity. So this guy became union of two different two things. So this is x m0 m1 m2, and this is x m0 m2 m4. So if you have this instanton here and here, then you can glue them together, and then goes up, and then you have another this break. And this gives the following. If you take the commutator of this M3 operations, then it is something like a difference between two associativity. So yeah, I mean x, y, z, x, y, z. So it's a failure of associativity is controlled by M3. So this is the usual pattern of infinity structures. So using this one parameter family of Riemannian metrics on X, M0, M1, M2, M3, then we can show that these M2 operations are actually associative. And so this gives M3. And now you can imagine how to do it in general. So just I wrote here. So now if you want to define M4, then you take this M4, then you take this all the, yeah. So you have this x0, x1, x2, one more, right? x3, x4, all this metric ribbon graph, ribbon tree. And if you have this metric ribbon tree, then you can make it fat a bit. Then somehow domain in R2 parameterized by this, in this case, parameterized by R2 itself. And then you can take the product with sigma and glue mi cross R, and you get this one parameter family, and that is x m0 blah 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 m4. So for any k, you can define this one family of Riemannian manifold, 4 manifold, and we can use this ASD connections, modular ASD connections, to get all MK operations. And it is a kind of standard, very similar to the proof of infinity relations in Lagrangian Floer theory, that this actually is infinity, satisfy infinity relations. So this is a gauge theory, one category. So let me summarize. So we have this infinity category whose object is a 3 manifold together with vector SO3 bound, which bounds sigma. And the space of morphism as a abelian group is a free abelian group generated by the set of flat connections of Mi and Mi plus 1. And higher composition map is count SD connections on this 4 manifold, which is obtained by some unparameter family of domain together with Mi cross R glued. So you have this 4 manifold and fix asymptotic boundary conditions and use SD connection to get the 4 manifold. So that is infinity category. So we can associate infinity category for any Riemann surface of even connected with even connected components. So that is one of these categories. So this is the gauge theory side of the category. So now I want to go to symplectic side, but that is a usual Lagrangian Floer theory. But actually, I need a bit more kind of stronger version than this usual thing. So we consider this sigma together with together with SO3 bundles. And we consider this moduli space of flat connections on this sigma of these bundles. And the cup product defines symplectic structures. And this is non-singular. So you have a smooth, compact symplectic manifold. And on this symplectic side is a object, is a pair L and B. And L is immersed Lagrangian submanifold. So immersed is somewhat important. So L goes to this R of sigma. It's half dimensions and the symplectic form is 0. But we need to assume that it is immersed. And B, as I explained, is a version of bounding cochain. And this is, I think, this immersed case is studied by Kaufman and Joyce, and we didn't invent the case, but this immersed case is important because actually this bounding cochain is 0 in an embedded case in our particular situations. So let me recall what is this bounding cochain in this case. So we have this Lagrangian submanifold, so contained in this R of sigma. Then B, in our particular case, is just a finite sum like this. What is this? So alpha I, so you have this finite sum, and a pair of alpha I and alpha prime. So maybe originally it comes from some spheres, right? And alpha I is somewhere here, and alpha I prime is here. So they are the same element of L. No, they are element of L which are different, but but they go to the same point here. So this alpha I goes here, and alpha I prime goes here. So basically, this is a set of all self-intersection points. And in our particular case, because of the monotonicity, bounding cochain just lies on this self-intersection point. So it is a finite sum with integer coefficients of this self-intersection points with appropriate index. So this is what this B means. And B satisfies some molar Cartans. So that is this object in a symplectic category. And I think L is monotone. So far it's monotone. So L is said to be monotone. What is it? So if you have this U, D2 boundary, which goes to X, L tilde. So we have an imagine. So L tilde goes to X and image is L. And U restricted to this boundary goes to L tilde. And interior, U itself, be better to write it. So you have this D2 and you have S1. And U go to X. But if you restrict it to S1, then it lifts to L tilde. Then for such a things, we assume something like Maslow index of U is proportional. I think there are some fixed number in our cases of the symplectic area. So I want to explain a bit more. So if you consider this kind of things, so suppose your L is something like this, then if U is something like this, so your U may be something like this, but then we don't assume this kind of relations. And this is something called the Maslov index. And if you do not know Maslov index, it is something like a relative version of first chunk class. So we don't assume this condition for this U because this boundary loop, in this case, this boundary loop, this does not drift. To this L tilde. So this does not, so this is not such a U. But if you consider, for example, for everything, maybe this part is double. So everything, then it drifts, then you assume this. So that is called a monotone immersed Lagrange sum manifold. And in a main context is the following. If you have this R of sigma, then you have this immersed Lagrange sum manifold, R of M. So boundary M is sigma. Then this is immersed. But this is actually a monotone in our sense. So in this case, it is not very bad, but it is monotone. And for the now this is an object in our setting, and it is I think established by Yongin Oh many years ago. Then in a monotone embedded Lagrange sum manifold, we don't need anything else to define Floer homology. But for the monotone immersed case, we need this kind of B to have a well-defined Floer homology, satisfying molar Cartans. So in our case, on the object is a pair of Lagrange sum manifold and the so-called bounding cochain, maybe better like positive bounding cochain, which satisfy molar Cartan equation. So that is an object of a symplectic category.
Sorry, Kenji, can I have,
yeah.
When you have several M's, do you have some kind of balancing or Bohr-Sommerfeld condition? How do you know that the Floer homology of a pair of R of M's is well behaved?
I think each individually has this B.
Okay.
And then Floer homology is well defined. So I think we don't use Bohr-Sommerfeld. This C is universally defined. So you have this monotone in this sense.
Yes.
And the B, which is positive in our sense, this finite sum,
Okay.
which satisfy molar Cartans. And you have a pair of such object, then you can define Floer homology. That I think general theory. It's a part of Akaho-Joyce's story.
No, but if you have more than two and you want the higher operations, then you could have infinite sums, right? For fixed generators, you could have infinitely many triangles or rectangles bounded by fixed monotone Lagrangians.
I think positivity is okay. This B is all, area of this B is actually all positive. So this kind of sum in our situation is easier and just the finite sum.
So what coefficients do you use? Do you have Novikov coefficients then?
No, we don't need, we can just use D.
That's positive.
I don't think I believe that. But anyway, we can discuss that later.
Yeah, because everything is monotone.
But it needs to be balanced also or something. If you have, anyway, we can discuss that later.
Yeah, maybe I need to define monotonicity a bit more precisely.
Yeah.
Actually, there is, so we have this something called the pre-quantum boundary. And this pre-quantum boundary in our situation comes with the sections restricted to each Lagrangians.
Okay.
That's Chan-Simon. So that's a stronger version of monotone.
Yes, it's exactly balanced monotone. Okay, you're okay.
Yeah. Okay, yeah. Thank you very much for corrections. Yeah, you just assume what I said, probably it's not enough.
Okay.
Thank you. Okay, so now there's a one theorem which should be written is the following. if you have a three-manifold M, whose boundary is sigma, and we have this E of sigma, W2 is a fundamental class, and you have boundary M, then if you have this immense Lagrangians, and then there exists some positive bounding cochain on these Lagrangians. So that's somewhat non-trivial statement. But this is something to be written, and this is a part of our project to prove this Atiyah-Floer conjecture itself, not this categorifications.
What is positive?
Positive means that you have this DI, right?
Yeah.
And this guy has some kind of energy functions, and we assume that energy function is positive. Yeah, so you have some monotone structures. That's another story. But your Floer homology in this situation has a Z filtered, and it is something similar to in a situation of the contact story. Everything is filtered, and all the generator has a filtrations, and all the self-intersection point is divided into positive one, negative one, and zero. Energy 0, 1. And we assume that the support of this bounding cochain lies on the positive part. That is positive. And that is related to what Denis asked. Using this kind of positivity, all the operations are just finite sum. Okay, so now I just want to say a few words about this statement. So there are intuitive understanding of this statement. Is that this bounding cochain is obtained by counting some instanton on M cross R. So in this case, M is regarded as a non-compact, means that M minus compact is sigma cross 0 infinity. So this is the picture of M cross R. So you have this R directions, and also you have this infinite directions here, end directions. And then you have this alpha I, beta I, that is flat connections on them. And we assume that they go to the same flat connections on sigma. So the story is, so the picture is something like this. So you have this R of M in R of sigma, and your point is something here. So this point is equal to this restrictions of sigma and also restriction of sigma, and alpha and beta are not equal on them. So for each point, we want to associate some number. That is our bounding cochain. And it is, I can believe that such a bounding cochain can be obtained by counting some instantons on this rather difficult manifold to analyze, non-compact 3 manifold cross R. And we assume that in the negative infinity, it converges to alpha R. Positive infinity, it converges to beta R. And in this another end, it converges this flat connection on sigma. And such a kind of counting should be this B. And there is an intuitive, somehow heuristic argument, but it's still difficult. But actually, such a modular space was studied by Gangu Bok-Sue, and he proved some part of the story on this modular space, but it's not yet completely proved that it is a bounding cochain. But we can, I think we believe we can prove the existence without using this modular space directly, but a bit more indirect way. So that is the story about these things. So now I want to explain one categorifications of the Floer conjecture. So you now see what it is. So you have these two infinity category. One is this gauge theory infinity category, whose object is three manifold, and morphism is Floer homology of glued three manifold, and operations are something like a family version of the instanton counting. And on the symplectic side, its object is a monotone Lagrangian submanifold plus some bounding, positive bounding cochain. And Floer homology is of this Lagrangian Floer homology obtained by using this bounding cochain. And the higher operation is something like counting polygons. So this isomorphism between instanton Floer homology and Lagrangian Floer homology is a usual Atiyah-Floer conjecture, which we believe we can prove, but not yet written. But then categorification is just these two can be kind of upgrade to the infinity functor, which gives an isomorphism on the cohomology of the morphisms. So this is something like a fully faithful embedding. And once we prove this, then the main thing we have to establish for this categorification is to show that all the operations here are compatible with all the operations here. And as you see that these operation on the gauge theory side is obtained counting instantons on some parameterized family of Riemannian metric. And this Lagrangian Floer homology, Lagrangian side, it is obtained by counting polygons. So it's at the beginning, it doesn't so much identical, but we believe we can prove this isomorphism, this existence of infinity functor. So this is one categorization of Battier-Floer conjecture. And I want to explain a few ideas how to prove this one categorization of Battier-Floer conjecture. So the idea is representations of infinity functors. So it's about the following things. So we consider this gauge theory one category, and we consider this symplectic side infinity category. And then we consider another DG category. It is actually a DG, another infinity category. It's a DG category of infinity module over this symplectic one. So I think infinity module is something like, you have a ring, then you have a light module, and you can just generalize the notions to infinity, light infinity modules. And there is a well-known functor that's called the Yoneda functor, which goes from this infinity category to the category of modules. And this is actually a fully faithful embedding, and that is called a Yoneda functor. So now the idea of the proof is twofold. First, we cook up this functor from this gauge theory category to the category of modules. That is the first step. And the second step is to show that for each object, then if you consider this here, and that object we want to prove to be is representable. It means that this module comes from some object in this S of sigma. Then you can lift this one to get an infinity functor. I think this idea we used already several times. Once in a correspondence story, and the other is in this Atiyah-Floer type things also. But this is the kind of things. And then the first thing I want to explain is how to obtain. So first thing is to obtain the following things. We have this gauge theory sigma category, and we have this module over this S sigma. And I want to construct infinity functor. Then if you think a bit carefully, this is equivalent. You have this infinity by module over the sigma and S sigma. I think this is, I can explain this very easily. So you have a ring. So A is a ring, B is a ring. Then you have a kind of A module to, so you have you have this AB bimodule. So you want to define functor from A module to B module. Then you can do this if you have a kind of M, A, B, right? This is the bimodule. Just the N goes to N tensor A, M, B, right? So what we need is to obtain this bimodule. So in our stations, so you have this gauge theory category and this symplectic category. So you want a bimodule of all these two categories. So how to obtain bimodule? So to obtain this bimodule, we use this something called a mixed moduli space. And this mixed moduli space is introduced by Max Lipinski. And we use it to some version of Battier-Floer conjecture, but we want to kind of more enhanced version of this mixed moduli space. So I want to explain this mixed moduli space because it does encompass some things. So we have this picture. Maybe you don't see what I'm writing. So what in situations, right? So you have this, yeah, you need me to construct AB bimodule, right? So we want to find SG. No, 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 no. We want to construct.
In S sigma, maybe.
Yeah. So we want to construct G sigma, S sigma bimodule. So what is this? So suppose you have this MI, M1 to MK. So it is an object here. So it means that the boundary M, it is three-manifold is sigma. And here you have this L1, LK. It is a Lagrangians in a space of flat connections. Then what we want to construct is something like a C, M1, MR, MK, and L1, LK. No, I'm sorry. No, I'm sorry.
You need morphisms. I mean, first
Yeah. First, what we need is just C, ML. This is a kind of abelian group. And then something we need next is the following things. So G sigma M1, M2 tensor G sigma MK minus 1, MK tensor C MK L1 tensor this Floer's chain complex L1, L2, blah, blah, blah. Floer's chain complex LK minus 1, LK. And this one goes to C, M1, LK, right? So this is a kind of N, K, I'm sorry, this is L. L. It is a structure of bimodule. So I want to define this kind of operations. And the idea is just to use this mixed moduli space. So now, yeah, I think, probably it's okay. So now we consider this space. So what is this? So X here is something like a four manifold. And it is a kind of together with family of Riemannian metric. And the boundary of X is a bit different. It is a kind of R cross sigma. So before I use something like a four manifold without boundary, but has an end. But here we have a four manifold which has a one boundary component. So what is X? So I just draw again. So I take this kind of picture. So we have this boundary, and others is something like this. So this is a domain in R2. And you know, this domain is something like a fattening of some trees, like this. There are one straight line, and the other is just a kind of, you know, you have many trees coming from this straight line, and then you make it fat. So you have this D. It has a family parameterized by the metric. And then we take this D cross sigma. So this is the four manifold. And it has many boundaries. But then for each of this part, you have this M1 cross R. So you glue it together here. And we take this M2 cross R, you glue it here. And M3 cross R, and you glue it here. Blah, blah, blah. So that is this X. So we glue all these boundaries. So these are no longer boundary. But it still remains one boundary component here. So X is a family of four manifold, and whose boundary is R cross sigma. So that is this one. Then if we consider this ASD anti-self-dual connections on this four manifold, which is A here. And then A, so A, so A, so X has several ends. So X minus compact is something like Mi minus 1 Mi cross 0 infinity. So then we use alpha I flat connection on this three manifold on the A as asymptotic boundary conditions. So for this A, so we have this alpha blah blah blah, and then so we have this A3 connection with boundary conditions, and then you have this another part. So another part is the following. So you have this part, and this part on this part you take this U. So U is a map from this strip. So strip is this strip is just 0, 1 cross R cross this space of flat connection on sigma. Maybe it's T and tau. No, this is T and this is tau. And then so we have this powers, and A is assumed to AST. So star FA plus FA is 0, and U is holomorphic. So D bar U is 0. And then so we fix this asymptotic boundary condition for A, and then for U we use this Lagrangians for the boundary conditions. So that is, I think, the same as usual Floer theory. So I just do it rather easily. So you have this U, right? And then here you have this L1, L2, L3. So then we assume U1 tau is L1 on this part. And then here you have this L0 and L3, blah, blah, blah. And this point fix point in L2 cap L3. So you require this goes to P. So that's the same as usual Floer theory. And then the most novel and interesting part is this line. So what is this line? So it's this line. Why this is important, interesting is that here you have gauge theory equations, and here you have a symplectic pseudo-harmonic curve equations. And on this on the intersection point, you require something called the mixed equations. So what it is? Yeah. So this is the mixed equations. So we have this A here minus T tau, and you have a U here for T tau. And then the mixed condition is the following. So you restrict, oops, if you restrict your connection A on X side to on this line, 0 tau plus sigma. So this point to this point, we require it is a flat connections on sigma. And if you take with gauge equivalence class, so it is an element of R of sigma. And U is a map to R of sigma. So we require that this gauge equivalence class is equal to the value of U here. So that is called the matching conditions. So now we have this moduli space of a pair. No.
Sorry, Kenji, I think you didn't tell us what the chain complex CML is to begin with, but I assume it's a flat connection on M whose restriction to sigma is also a point of L. Is that right?
Yeah. So that is what I wrote here. Yeah.
No, but the condition at top, at tau goes to plus minus infinity.
Yeah, plus and minus, yes. So that I didn't yet explain, yes. Okay, so now we have some other, yes. That is a kind of mix, so-called a mixed end. So you have in this kind of situations, this is MK, and this is a part of X, and this is a U, and this is a L1. And then on this one, then, you said. So A, so limit tau go to minus infinity a is asymptotic to some a alpha, so that alpha is flat connections on M, and its gauge equivalence class is equal to limit tau minus infinity of u. And the same conditions for tau go to plus infinity. Yes, you are right. So you have this alpha and you have a beta. So you have many things here. And so this is a mixed moduli space. And yeah, this is enough confusing, but so what we need to fix, right, to get, so you need to alpha AI is a flat connections on mi minus 1, mi, and pj is a lj minus 1 cap lj, and alpha is a kind of k cap l1, and beta is a rm1 cap ll. So now this mixed moduli space gives if the dimension is correct, gives a number for such a I, B, J, alpha, beta. And this number should be M, N, alpha 1, beta, A, K, alpha, P1, PL, and its coefficient at beta. So this is a definition of the bimodule structure. And you will see that how this picture, so this is the definition of N. And actually, so basic package to build this mixed moduli space is written in our recent paper published GAFA with Alekaba Daime and Max Lipiansky. And that is a very simple case, like just a much simpler case. But, you know, we include many other integrants, but basically the main part is the same. So we can just make it a bit more general so that this moduli space has a good structure. You can count it. Okay. And of course, this is based on Lipiansky's earlier paper. So now, what we need to know is that if you just look this family of Riemannian metrics on this kind of things, and then how it will behave, and then you just look which kind of infinite end of this kind of moduli space has, then you get this bimodule structure. Okay. So now this is a definition of the infinity functor. To be, you can see that to write it up is a bit cumbersome, but we have to do it. So now the claim is the representability. What is the representability? So if you have a M, so that the boundary M is sigma, and then we consider this, so object M, so this gives a module, S sigma module. And then our claim is that this S sigma module lies on an image of Yoneda functor. It means that representable. And I don't want to explain the proof, but once we can prove it, then this is already an infinity functor. And this Yoneda functor is a homotopy equivalence to the fully phase category. Then once this one is containing an image of this, then you don't need to do anything about the morphism. Then you can just lift it to get the infinity functors. Okay. So now rather to explain the claim or go to two categorizations, I want to say a few words, a possible application of this kind of things. So I want to, I think I have at least one potential way to apply this. It is a finding generator of this category. So you have this G of sigma, and it is a infinity category whose object is all three manifold. That's rather a difficult thing. And all infinity relations are just the instanton counting of some family of Riemannian manifold. It should be very difficult to calculate. So I want to find a generator of the infinity category because recent development of homological mirror symmetry shows that the finding generator is probably the way to calculate the infinity category. So suppose you have this genus G Riemann surface. Then you have some analog of handle body. So this mg whose boundary is this sigma z and t2. So, and then you have this most functions so that the genus is always increased. So it's something like this, right? You have the t2, then you have genus 2, genus 3. So you have never go up and down. You have this. So this is something like a handle body. So some kind of SO3 analog of handle body. Then the conjecture is that there exists finitely many of such a handle body, so that it generates our category. And probably it is more even better that we can specify which finitely many of such a handle body is necessary. And I want to say that to prove this directly in a symplectic side might be, gauge theory side might be difficult because we don't know so many about this infinity structure and gauge theory side. But if you go use this at your Floer conjecture to go to symplectic side, so this means that you need to find a infinity category for this S of sigma. It's just infinity category of space of flat connections. And but that by Mohammed Abzai, there are various ways to establish some generating things. So I believe one can use this knowledge about cohomology of the space of flat connections to obtain some nice finite set of handle body which generated. I cannot do it yet, but this is a possible application. Thank you very much. I stop here.
Questions? Okay.
Kenji, that inclusion of links create a problem.
I don't understand. Could you repeat?
Links in manifold.
Link?
Yeah.
What about?
Yeah, I mean, if two categories of them.
No, but links is manifolds with boundary.
No, additional structural understanding of links which should accept your boundary.
But links that intersect with boundary?
Yeah, like in terms of violent break.
So tangles. Then.
Yeah, tangles.
Nice.
Well, it's beyond. It's
three categories.
So you want to include some knot kind of things?
Yeah, this kind of.
Yeah, I believe there is such a version, but we didn't. I think there are work by Kronheimer-Mrowka type things, and that should be related to these versions. One consider some kind of connections with some singularity along the knot, and the gauge theory of such a thing would give this Kronheimer-Mrowka type things.
Maxim?
Yeah. So it also, can you extend it? Do you have a hope that it could be extended to kind of all three manifolds and all surfaces? Yeah. No, I mean also without this conditions of Stiefel-Wheatley class when you get you got single symplectic manifolds. So just the full QPFT up to dimension 2.
I mean, to generalize this to the case of flat connect, some reducibles, we need to use some equivariant business. And basically, we know how what should be, but the analysis is still very difficult. The hardest thing is that to establish this mixed moduli space in a reasonable way, we heavily use the conditions that there is no reducibles occurs in this bad line, mixed boundary condition line. I tried, and also probably Piansky tried to prove that kind of things, and even this removable singularity, I feel I still need this irreducibility. I hope in future we can do it, but it's still far away.
Yes. So can you explain a bit more on how we define the symplectic structure on R sigma?
It is just you have this tangent space is the H1 with local coefficients. Then you have a cup product and integrations using trace. And since it is a one form, so it is antisymmetric. And the basic theorem is that this antisymmetric form is actually closed.
With character variety.
Yeah, that's also Kähler manifold, actually. Even project algebraic variety.
Thank you.
Yes.
So I'm sorry to ask a very basic question because you spoke about perturbations, certain spaces. Now, when you look, for example, in some cases, for instance, on Floer homology, you look at the flat connections on your bundle and you say it's a finite space after perturbation. But originally, you have C infinity different automorphisms which send the flat connections to many others. So what kind of perturbation do you?
I think, the perturbation of the equation that the flat is established by Floer and Donaldson, that uses something called the holonomy perturbations. So we study the set of all, so we approximate by the space of all connections by finite dimensional space of kind of element of SO3 by just using sufficiently many closed loops and taking holonomy. And then you take some functions. That's called holonomy perturbations. That we can use in this case.
So it's so the number depends on the perturbation.
Yes, yes.
Okay.
But one can show that it's homology. I mean, number of flat connections depends, but the Floer homology is independent. That's usually the case of Floer homology.
Okay, so another question, this definition of the category G sigma. So you, for the higher compositions, you said that you have like a one parameter family of 4 manifolds. And then
K minus parameters. K minus 2 parameters.
Okay, let us say in the first node for M4, I think, any case. And then you want to get some, so you look at anti-self dual connections, but for a fixed parameter or for on the wall thing? Or?
All the parameters. That's important. Moving the parameters.
You
So the
let
dimension,
but you want it to be anti-self dual for one of the metrics in this family.
Only for one?
No, for any metric in this family.
And this is a finite space?
This is going to be finite because for a generic metric, you would have no solutions. And you expect that as you let the metric vary, there will be isolated choices of metrics in the family where there are solutions.
It's a metric on the total space.
No, on the four manifold.
on X, on a whole manifold, yes.
Or manifolds.
It's a single four manifold with a family of metrics. They all look the same. They're all diffeomorphic.
Okay, so you count the parameter values for which there is an anti-self.
Exactly.
And you have to count it with a sign.
Yes, everything. Yeah.
Yes, as usual, yes.
Okay. And this is related to which homology? To the symplectic or the instanton?
No,
Instanton.
This is again side. In a symplectic side, it is related to this counting of polygons. That's a part of the main part of the conjecture.
This is the categorification of which side?
No, it's not a categorification. It's higher products. We can discuss this slide. It's probably easier to discuss this slide. Okay. All right. There's no further questions. Let's thank Kenji again.
Thank you.